And the last one in the graphs, which is a simpler one again. I think the first thing I'll do again is maybe factorise that top, since I can see it factorises. X times x, 1 times 3, plus to the bigger, and negative to keep the signs opposite. Then I'll say what have I got, right? Where does it cut the axis? It cuts the y-axis if x is 0, and if x is 0, I'm left with negative 3 upon 1. So that's negative 3. So I've got the point 0, negative 3. Where does it cut the x-axis? It cuts the x-axis if y is 0. That means that the numerator part is sufficient to be equal to 0, which means that x equals negative 3, put them in order, or x equals 1. So I've got the points negative 3, 0 and 1, 0. Next part, I'll just highlight that so far. So far I've got where it cuts the axis. These 3 points. Next, any asymptotes? Yes, because it's a rational function, I've got a denominator. So vertical asymptote, that will happen if the denominator is ever equal to 0, and it will be, at x equals negative 1. What happens there? Well, I could do it in bits and pieces, or I could make up a table of signs, or I could make up just a partial table of signs just to see what happens here. I think that's what I'll do to the side here then. So, for x, what happens at negative 1? Well, it's made up of these 3 factors. The actual value comes from the values, the signs of these 3 factors. Doesn't matter if they're multiplying or dividing, just treat them as just the product of the 3 factors. I know that at negative 1, there's a break there, it just goes off. It's not defined, but I'm just going to write infinite, and then I'll find the value of the sign on either side of it. Well, negative 1 plus 3 is going to give a 2, so either side of it is still going to be positive, if you just want to change it a bit. At negative 1 it'll be negative 2, just change it a bit, it'll still be negative either side of it. But here it's sensitive, at negative 1, that's when that term becomes 0. Put it onto this side, it'll be negative, on that side it'll be positive. So what that says is, it's going to be positive on that side and negative on that side, so that's the way it's heading off then. Which means on this side it's going up towards, and this side is going down towards negative infinity. That's the approaches. Next part, what about the non-vertical asymptote? Well, in a case like that, because I've got a top-heavy fraction here, I'm going to do a division. I'll divide it in. X plus 1 will divide into x squared plus 2x minus 3. So I need one lot of x to make that x squared, put it in the right column, so x squared plus x, leaves me a single x minus 3, and then I just need a 1 to make the x into an x. Subtract, negative 3, take away 1, negative 4. So that means this can be written as y equals x plus 1 minus 4 over, I was dividing by also x plus 1. Then I can say, as x tends to infinity, that means that y would tend to this x plus 1, because this part would just become 0. Dividing by a very large number, that fraction would disappear. How does it approach that? I'll put it over here. As x goes to negative infinity, y would go to, don't tamper with that expression, this part would then be take away a negative, x is the dominant term, that'll be plus a bit. As x tends to positive infinity, y is going to go to, again just leave this bit alone, but that'll be positive, so it's take away a bit. So for this line x plus 1, which I'll draw like this, y equals x plus 1, it says that heading towards the negative end of the x, I'm going to be above the line, but getting closer. And heading towards the positive end of the x, I'm going to be a bit below the line, a line minus a bit, but getting closer. So that's that part, so I've got quite a bit so far. Next would be stationary points. I want the derivative. Right, dy by dx then. I'll differentiate this thing, that's much easier. So that'll just be a 1, and then that will be, that's power negative 1, so I'll turn into multiply by the power, so it'll be plus 4, take 1 off the power, it'll now be negative 2 or 2 underneath, and straight away that can never be negative. That's always positive. The lowest that can come to would be 1. So I can say dy by dx is always greater than 0, which means it's always increasing. no stationary points, always increasing. Further, I could do this. What's the second derivative? Just for fun. The second derivative would be that bit would disappear, multiply by the power, so it's negative 2 times it, so it's negative 8 over x plus 1 cubed. Well, one thing you can say straight away about that is, okay, I'll change signs, but that can never be 0. The second derivative can never be 0, so I know there's no points of inflection, if I was interested in identifying them anyway in the first place. Right, let's put that together. So, here's my axis. What have I got? It cuts the y-axis at negative 3. Let's put that about there. It cuts the x-axis at negative 3. It cuts the other part of the x-axis at 1. It's got a vertical asymptote at negative 1. I should maybe really put that in dotted. And it's got a non-vertical asymptote of y equals x plus 1. Well, that means I'll go through there as well. Right, so going something like this. Y equals x plus 1. Don't really need to show that cuts at 1 and negative 1. They're not points in the graph. There we go. Then, how does it snake through them all? Right, it should approach the vertical asymptote on this side from above. And it should approach that line from above. And it should cross through there. Oh, that's going to be a bit messy, because it's going to come down. I'm going to move that negative 3 just to make it easier for me to draw. So it's going to come down like this, where it was crossing at negative 3. On this side, it's got to go from below the asymptote to below the line, crossing at 1. Work. Something like that. That would be the graph, looking like this. From the derivative, it was always increasing, it always is increasing. This graph is always heading upwards. It's got the two different concavities, but no points of inflection. Here it is.